To comprehend the clinical complexities of menopausal hormone therapy, one must first grasp the intricate biological and endocrine shifts that define the menopausal transition. This period is not merely the end of menstruation, but a fundamental rewiring of a woman's hormonal milieu driven by the depletion of ovarian reserves. The decline of key hormones, particularly estrogen and progesterone, initiates a cascade of physiological changes that manifest as the familiar symptoms of menopause and contribute to an accelerated risk for several chronic diseases of aging. The rationale for MHT is rooted directly in this biological foundation, an attempt to restore hormonal balance and mitigate the systemic consequences of its loss. Show your support for women's health with a quick like, share, and subscribe. The hormonal cascade, the central roles of estrogen and progesterone. The female reproductive system is orchestrated by a delicate interplay of hormones, with estrogen and progesterone serving as the primary conductors. Their synthesis, function, and interaction with specific cellular receptors are central to reproductive health and have profound effects on nearly every organ system in the body. Estrogens are a class of steroid hormones essential for the development and regulation of the female reproductive system and secondary sexual characteristics. In humans, there are three principal endogenous estrogens: estrone, E1, 17B estradiol, and estriol. All are synthesized from cholesterol precursors through a series of enzymatic steps. The most potent of these, 17B estradiol, is the predominant estrogen produced by the granulosa cells of the ovarian follicles during the reproductive years. Its synthesis involves the conversion of androgens to estrogens, a rate-limiting step catalyzed by the critical enzyme aromatase. After menopause, with the cessation of ovarian follicular activity, the primary source of estrogen shifts to peripheral tissues, such as adipose tissue, where aromatase converts adrenal androgens into the less potent estrone. The physiological actions of estrogens are mediated primarily through two high-affinity nuclear receptors: estrogen receptor alpha, ER-alpha, and estrogen receptor beta. These receptors are ligand-activated transcription factors that, upon binding to estrogen, dimerize and translocate to the cell nucleus to regulate the expression of target genes. They are encoded by separate genes on different chromosomes: ESR1 on chromosome 6 for ER-alpha, and ESR2 on chromosome 114 for ERB, and possess distinct, though sometimes overlapping, tissue distributions. ER-alpha is the predominant receptor in the uterus, mammary glands, ovaries, the claw cells, and bone tissues classically associated with reproductive function and hormonal cancers. In contrast, ERB is more highly expressed in the prostate, bladder, colon, immune system, and ovarian granulosa cells. Both receptors are co-expressed in the cardiovascular and central nervous systems. Crucially, these two receptors can have different and often opposing biological functions. ER-alpha is generally associated with the proliferative effects of estrogen, driving cell growth in tissues like the endometrium and breast. ERB, on the other hand, often serves as a physiological antagonist to ER-alpha, exerting anti-proliferative and tumor-suppressive effects. This fundamental biological tension, the dual and sometimes contradictory nature of estrogen signaling through its two main receptors, lies at the heart of the MHT risk-benefit paradox. It explains how estrogen can be protective in some tissues, like bone and blood vessels, while simultaneously posing a risk in others, like the breast and endometrium, a reality that has fueled decades of clinical controversy. Progesterone, the other key female sex hormone, is primarily known for its role in the menstrual cycle and pregnancy. Produced by the corpus luteum after ovulation, its main function is to prepare the endometrium for embryo implantation and to maintain pregnancy. It achieves this by counteracting the proliferative effects of estrogen on the uterine lining, inducing secretory changes that make the endometrium receptive. However, the physiological effects of progesterone extend far beyond the uterus. It serves as a crucial precursor in the steroidogenic pathway for the synthesis of other hormones, including estrogens, androgens, and corticosteroids. Progesterone also has significant immunomodulatory effects, helping to establish maternal tolerance to the fetal semi-allograft during pregnancy, an action mediated in part by the progesterone-induced blocking factor. Furthermore, progesterone receptors are found throughout the central nervous system, where the hormone exerts neuroprotective effects, and it plays a role in mammary gland development and bone formation. The menopausal transition, or perimenopause, is defined by a series of predictable yet individually variable endocrine changes driven by the progressive decline of the ovarian follicular reserve. This process culminates in the final menstrual period and the establishment of a new, stable, low-estrogen postmenopausal state. A woman is born with a finite number of ovarian follicles, and this pool is steadily depleted throughout her reproductive life. This process of ovarian aging begins to accelerate in the mid to late 30s. Menopause occurs when the number of remaining follicles drops below a critical threshold of approximately 1,000, at which point the ovaries are no longer able to sustain regular ovulatory cycles. During the reproductive years, the hypothalamo-pituitary-ovarian HPO axis operates as a tightly regulated negative feedback loop. The hypothalamus releases gonadotropin-releasing hormone, GnRH, which stimulates the pituitary to release follicle-stimulating hormone, FSH, and luteinizing hormone, LH. These gonadotropins in turn stimulate the ovarian follicles to produce estradiol and the peptide hormone, inhibin B. Estradiol and inhibin B then feed back to the pituitary and hypothalamus to suppress FSH and LH secretion, completing the loop. The earliest detectable endocrine sign of reproductive aging is a selective fall in inhibin B, which is a direct product of the diminishing number of follicular granulosa cells. The reduction in inhibin B removes one of the key brakes on FSH production, leading to a compensatory rise in early follicular phase FSH levels. This elevated FSH acts as a stronger stimulus on the remaining follicles, which initially allows estradiol levels to be maintained or even slightly elevated, preserving regular cycles for a time. However, as the follicular pool dwindles further, the ovaries become less responsive to FSH stimulation. This leads to erratic follicular development, anovulatory cycles, and the characteristic hormonal instability of the menopausal transition, with wide fluctuations in estradiol levels and irregular menstrual bleeding. Following the final menstrual period, a new hormonal equilibrium is established. Ovarian production of estradiol and inhibin B ceases, leading to very low circulating levels of these hormones. The loss of this negative feedback results in persistently and markedly elevated levels of FSH and L. While testosterone levels also decline with age, the drop is more gradual and not specifically tied to the menopausal transition, resulting in a state of relative hyperandrogenism, a higher androgen to estrogen ratio in postmenopausal women. The pathophysiology of menopausal sequelae, from vasomotor symptoms to bone density loss, the profound drop in circulating estradiol is the direct cause of the most common symptoms and long-term health risks associated with menopause. These sequelae are not isolated events, but rather interconnected consequences of a single underlying biological trigger, positioning the menopausal transition as a critical inflection point for the acceleration of chronic disease. Hot flashes, or vasomotor symptoms, VMS, are the cardinal symptom of menopause, affecting up to 75% of women. They are not caused by an actual increase in the body's core temperature but by a dysfunction in the central thermoregulatory center located in the hypothalamus. Estrogen withdrawal leads to a narrowing of the thermoneutral zone, the narrow range of core body temperature that the body maintains without initiating sweating or shivering. In symptomatic menopausal women, this zone is so constricted that minor fluctuations in core body temperature, which would normally go unnoticed, now cross the upper threshold for heat dissipation. This triggers an abrupt and exaggerated physiological response, profuse sweating, peripheral vasodilation, leading to flushing of the skin, and an intense subjective sensation of heat. This neuroendocrine dysregulation is thought to be mediated by changes in central neurotransmitters, particularly an increase in norepinephrine activity. The physiological cascade of a hot flash, including increased heart rate and anxiety, is often accompanied by sleep disruption, which in turn can exacerbate other menopausal symptoms like mood swings, fatigue, and cognitive difficulties, illustrating the deeply interconnected nature of the menopausal experience. The tissues of the vagina, vulva, urethra, and bladder trigone are rich in estrogen receptors and are highly dependent on estrogen for their health and function. The hypoestrogenic state of menopause leads to a constellation of atrophic changes now termed genitourinary syndrome of menopause, GSM. These changes include thinning of the vaginal epithelium, loss of collagen and elastin, reduced blood flow, and decreased lubrication. This results in a less acidic vaginal pH, which alters the vaginal microbiome and increases susceptibility to infection. Clinically, these anatomical and physiological changes manifest as symptoms of vaginal dryness, burning, itching, dyspareunia, painful intercourse, and urinary symptoms, such as urgency, frequency, and recurrent urinary tract infection. Estrogen is a critical regulator of bone remodeling, the continuous process of old bone resorption and new bone formation. It maintains skeletal health by promoting the function and survival of osteoblasts, bone-forming cells, and crucially by inhibiting the activity and promoting the apoptosis programmed cell death of osteoclasts, bone-resorbing cells. A key molecular mechanism for this is the RANK-LOPG signaling pathway. Osteoblasts produce RANK-L receptor activator of nuclear factor kappa B ligand, which binds to the RANK receptor on osteoclast precursors, stimulating their differentiation and activation. Osteoblasts also produce osteoprotogerin, OPG, a decoy receptor that binds to RANK-L and prevents it from activating RANK, thereby inhibiting bone resorption. Estrogen tips this balance in favor of bone formation by suppressing the production of RANK-L and increasing the production of OPG. With the loss of estrogen at menopause, this delicate balance is disrupted. RANK-L expression increases while OPG decreases, leading to a surge in osteoclast formation activity and lifespan. Concurrently, osteoblast apoptosis increases. The net result is that bone resorption dramatically outpaces bone formation, leading to a rapid loss of bone mineral density and a deterioration of the bone's microarchitecture. This process significantly increases the risk of osteoporosis and fragility fractures in postmenopausal women. The rise and fall of an elixir, a history of hormone therapy before The story of menopausal hormone therapy prior to the watershed year of 2002 is a compelling narrative of scientific innovation, cultural transformation, and commercial influence. It traces the journey of a class of drugs from laboratory curiosities to one of the most widely prescribed medications in the world, hailed not just as a treatment for symptoms, but as a veritable fountain of youth. This history is characterized by a powerful treatment imperative that often outpaced rigorous scientific evidence, a pattern of reactive problem-solving, and an underlying unrecognized flaw in the observational data that propped up its widespread use, a flaw that would be dramatically exposed by the Women's Health Initiative. Early discoveries and the dawn of synthetic hormones. The scientific underpinnings of hormone therapy date back to the 19th century with Claude Bernard's concept of internal secretions, which laid the groundwork for modern endocrinology. By 1897, clinicians were already using crude ovarian extracts to treat menopausal hot flashes. A major breakthrough occurred in 1929, when biochemist Edward Doisy and his colleagues isolated and identified the chemical structure of estrogen. This discovery paved the way for the first commercial estrogen products. Initially, a preparation called Emanen, derived from the costly and limited supply of human placentas, was used to treat menstrual cramp. A more scalable solution arrived in 1942, with the FDA approval of Premarin, a mixture of conjugated equine estrogens, CE extracted from the urine of pregnant mares. This product made estrogen therapy widely available for the first time, specifically for the treatment of menopausal hot flash. The development of progesterone therapies followed a similar path of innovation. Natural progesterone was initially difficult to extract from animal sources and prohibitively expensive, costing up to $1,000 per gram, and requiring painful injections, limiting its use to the ultra-wealthy and racehorse breed. The critical turning point came in 1943, when chemist Russell Marker developed a process, later known as the Marker degradation, to synthesize progesterone from plant sterols found in a specific species of Mexican yam, the cabeza de. This innovation dramatically lowered the cost and enabled mass production. The final step was achieved in the early 1950s when chemists Carl Djerassi and Frank Colton, working independently, created potent, orally active synthetic versions of progesterone, known as These discoveries provided the complete hormonal toolkit necessary for the widespread adoption of MHT. The Feminine Forever era. Marketing, medicalization, and mass adoption. The availability of affordable, orally active hormones coincided with a profound cultural and medical shift in the perception of menopause. This transformation was powerfully shaped by commercial and cultural narratives that reframed a natural life stage as a pathological condition requiring medical intervention. At the epicenter of this movement was New York gynecologist Robert A. Wilson. His 1966 best-selling book Feminine Forever was a cultural phenomenon that cast menopause as a deficiency disease that was curable and totally preventable with estrogen. Wilson's writing was laden with alarming and misogynistic assertions, claiming that without estrogen, a woman's breasts and genital organs will not shrivel. She will be much more pleasant to live with, and will not become dull and unattractive. The marketing of the era echoed these sentiments, with advertisements aimed directly at husbands, assuring them that Premarin would make their wives pleasant to live with once again. This campaign was extraordinarily successful, leading to a quadrupling of MHT sales in the years after the book's release. The influence of this narrative was so pervasive that it shaped medical textbooks and clinical practice for a generation. It was later revealed, however, that this was not an organic medical movement. In 2002, Wilson's son disclosed that his father's work, including the book and his research foundation, had been financed by the pharmaceutical company Wyeth, the manufacturer of Premarin. This industry-funded campaign represents a classic example of how a compelling, commercially backed narrative can create a powerful treatment paradigm, even in the absence of rigorous, long-term safety and efficacy data. The progestogen pivot, addressing the endometrial cancer risk. The unbridled enthusiasm for estrogen therapy encountered its first major scientific obstacle in the mid. A growing body of evidence demonstrated a clear and alarming link between the use of unopposed estrogen administered without a progestogen, and a dramatically increased risk of endometrial cancer in women with an intact uterus. Studies showed that the risk was elevated 4 to 10-fold depending on the duration of use, as estrogen's proliferative effect on the uterine lining went unchecked. This discovery led to a sharp decline in Premarin sales and threatened the future of The crisis spurred further research, which soon provided a solution. Adding a progestogen to the regimen for at least 10 to 12 days per month could counteract estrogen's effect on the endometrium and mitigate the cancer risk. This led to the development and widespread adoption of combined estrogen-progestin therapy (EPT) for women with a uterus, reviving the popularity of MHT. This episode established a pattern of reactive science in the field of MHT, where a serious risk was identified only after years of widespread clinical use, and a solution was developed in response to the crisis, rather than through proactive anticipatory research. The apex of acceptance, MHT as a panacea for chronic disease. With the endometrial cancer risk seemingly solved, MHT use surged through the 1980s and 1990s, propelled by a new and even more ambitious promise: the prevention of chronic disease. The narrative shifted from feminine forever to healthy forever. Observational studies suggested that MHT could prevent the bone loss associated with menopause, leading the FDA to approve it for osteoporosis prevention. The most powerful driver of its popularity, however, was the belief that MHT protected women against cardiovascular disease. More than 30 observational studies, most notably the large and influential Nurses' Health Study, reported that women taking MHT had a significantly lower risk of coronary heart disease. Fueled by this promising but ultimately flawed evidence, MHT became one of the most prescribed treatments in the United States. By 1992, Premarin was the nation's top-selling drug, and by the late 1990s, nearly 15 million American women were using an estrogen-based therapy. Medical societies began to recommend MHT for the primary prevention of chronic conditions. However, this widespread belief was built on a foundation of observational data that was inherently susceptible to a critical hidden flaw: the healthy user bias. Women who chose to take MHT were on average healthier, wealthier, more educated, and more proactive about their health than those who did not. Their better cardiovascular outcomes may have been a reflection of these pre-existing advantages, rather than a direct effect of the hormone. This fundamental weakness in the evidence base set the stage for a dramatic and painful reckoning, when the therapy was finally subjected to the rigor of a large-scale randomized controlled trial, the Women's Health Initiative. In the history of menopausal medicine, no single event has had a more profound and lasting impact than the Women's Health Initiative, National Institutes of Health, NIH. It was an unprecedented undertaking designed to bring the highest level of scientific rigor to the pressing questions of postmenopausal health. Its hormone therapy trials were intended to definitively confirm the widely presumed benefits of MHT, particularly for cardiovascular disease prevention. Instead, the results, released in 2002, sent shockwaves through the medical community and the public, shattering the prevailing paradigm, triggering a global retreat from hormone use, and ultimately forcing a complete re-evaluation of the therapy's risks and benefits. Study design and rationale: an unprecedented investigation into women's health, The WHI was the largest and most expensive study of women's health ever conducted, with a budget of It was a multifaceted project that included an observational study and a large clinical trial component with 3 arms: dietary modification, calcium and vitamin D supplementation, and hormone therapy. The primary objective of the HT trials was to determine the long-term effects of MHT on the prevention of chronic diseases. The main outcome of interest was coronary heart disease, CHD, with invasive breast cancer designated as the primary adverse outcome to be monitored. The study enrolled a total of 27,347 healthy postmenopausal women between the ages of 50 and 79 at 40 clinical centers across the United States. A critical element of the study's design was its division into 2 separate parallel, randomized, double-blind, placebo-controlled trials based on a woman's uterine status. The estrogen plus progestin, E plus P trial. This arm enrolled 16,608 women who had an intact uterus. Participants were randomly assigned to receive or a placebo or a single fixed-dose combination pill containing 0.625 mg of conjugated equine estrogens, CEE, and 2.5 mg of medroxyprogesterone acetate, MPA. This formulation, marketed as Prempro, was one of the most commonly prescribed at the time. 2. The estrogen alone E alone trial. This arm enrolled 10,739 women who had previously undergone a hysterectomy. Participants were randomly assigned to receive or a placebo or a pill containing 0.625 mg of CE alone, Premarin daily. A central and ultimately decisive feature of the WHI was the demographic profile of its participants. The average age at enrollment was 63 and 2/3 of the women were over the age of 6. This meant that the vast majority of participants began hormone therapy more than a decade after their final menstrual period. This created a fundamental mismatch between the study population, older, asymptomatic, late initiators, and the typical clinical patient, who is a younger, symptomatic woman starting MHT at or near the onset of menopause. This discrepancy would prove to be the primary source of the confusion and controversy that followed. The 2002 bombshell, findings from the estrogen plus progestin trial. On July 9, 2002, the NIH abruptly announced that it was halting the E plus P arm of the WHI trial, approximately 3 years ahead of schedule. The study's Independent Data and Safety Monitoring Board had concluded that the overall health risks of the combined hormone therapy exceeded its benefits, primarily because the trial had crossed a pre-specified boundary for an increase in invasive breast cancer. The findings, published simultaneously in the Journal of the American Medical Association (JAMA), directly contradicted decades of observational data and clinical belief. The report showed that, compared to women taking a placebo, those in the E plus P group experienced statistically significant increases in the risk of several serious conditions, but also some benefit. The overarching conclusion of the investigators was stark. For the population studied, combined estrogen plus progestin therapy did not confer the expected cardiovascular protection, and in fact, caused a net increase in harm. They recommended that this specific therapy should not be initiated or continued for the primary prevention of chronic diseases. The release of the WHI findings was met with what has been described as unprecedented media coverage that created a climate of panic and hysteria among both the public and the medical profession. The communication of the results, both by the media and by the study's initial press materials, played a crucial role in shaping the subsequent fallout. The reporting overwhelmingly focused on relative risk statistics, which, while technically accurate, can be misleading without the context of absolute risk. Headlines emphasized a 26% increase in breast cancer risk, or a 29% increase in heart disease risk, creating a perception of grave danger. The absolute risks, however, were very small. For instance, the increased breast cancer risk translated to only 8 additional cases per 10,000 women per year of use. This critical context was largely lost in the sensationalized coverage. The nuances of the study design were also overlooked. The fact that the trial tested only one specific, older formulation of oral MHT in a predominantly older population was rarely highlighted. Instead, the results were broadly and incorrectly applied to all forms of hormone therapy in all women, at all ages. This overgeneralization was compounded by a statement in the WHI's own initial press release, which asserted that the adverse effects of estrogen plus progestin applied to all women, irrespective of age, ethnicity, or prior disease status. MHT prescriptions plummeted by as much as 80% in the United States and around the world. Millions of women, fearing for their health, stopped taking their medication, often abrupt. Physicians, faced with alarming headlines and the threat of litigation, became reluctant to prescribe MHT even for women with severe debilitating symptoms. The chill on hormone therapy was so profound that in the years following the 2002 announcement, researchers documented a statistically significant increase in the rate of hip fractures among women who had discontinued their therapy.